Hello, this is the second video on chapter 8, and I'm going to continue with a confidence interval and talk about t distribution and also confidence interval for proportion. All right, so let's get started. And let's go here. That's where I stopped last time. So what we have here is that before we talked about that if you have a population that we know sigma of the population, so this is known, then we take a sample of size n and we find x bar, and then we're going to assume that x bars make a normal distribution with the mean of the x bars is the mean of the population, and the standard deviation of the x bars is the standard deviation of the population divided by square root of n. Then we said, okay, these are x bars. Now, are we going to report x bar, that basically x bar is mu that we don't know? No, we're not going to do that. Well, what are we going to do? We're going to say we know we are certain percentage confident. Now, that's a confidence level. So our confidence level is at, let's say, CL. That's the confidence level. Suppose you want it to be 95%. So basically, you're going to say, okay, I want 95% of this. I want to know how far do I go to the right and how far do I go to the left to include 95% of possible x bars that I can get if I keep taking samples of this size, right? If I keep taking samples, 95% of them will be between what number and what number. And to answer that question, we went to Z and we said, okay, under Z, which is the standard normal, what are the two numbers? How far do I go to the right of 0? How many standard deviation to the right? How many standard deviation to the right gives me 95% in the middle? And we know those two numbers are negative 1.96 and 1.96. So then we go back here, we say, okay, so this number has to be this many standard deviations to the left of the mean, and this number has to be this many standard deviations to the right of the mean. So that means we write the mean plus and minus how many standard deviation is called z sub c, or we call it z sub alpha over 2, right? Alpha over 2. All right, so now our z sub c in this case, of course, is 1.96. And then how many standard deviation? Standard deviation is given by this, right? All right, that's the standard deviation of x bars, right? But here's the problem. For this section, we can do the same thing, okay? So what we can do is we can think of a population, but this time sigma is not known, and of course mu is not known. We want to find it. So if you take samples of this size, certain size, and then find x bar, well, then the distribution of x bars here will be, the mu of it will be the same as mu, but what is the standard deviation? Well, the standard deviation over square root of n, but we don't have the standard deviation of the population. So what do we have to do? Well, people used S instead. So that's the standard deviation of the sample. So they used S. But they realized that when they converted the x bars, so if you take the x bar and subtract mu, and divide by s over square root of n, you're not going to get z here. You're going to get something we call t, and the distributions of these t's doesn't look like distribution of z's, but it looks like distributions of t's. And distribution of t distribution is very similar to normal distribution. The mean is 0, but there is no standard deviation. So people realized that every time they took a sample, depending on what sample size was, the shape of this distribution changed. So for every sample size, they have a shape. So instead of talking about the standard deviation here, we talk about something called degrees of freedom, which is sample size minus 1. So if you take a sample size of 15, then 15 minus 1 is 14, then we're going to have a distribution that is t distribution with degrees of freedom of 14. Okay? So that's the idea we're going to use. So instead of using z to figure out how many standard deviations we have to go to the left and right of x bar, so we have the same idea here, x bar plus and minus, certain number of standard deviations, and the standard deviations are given by, the standard deviation of x bar is given by that, right? So how many standard deviations? Well, that would be t sub c or t sub alpha over 2, right? Alpha is how much is in the tails, right? Alpha is how much is in the tails, and half of it is how much is in one tail. So we can find these numbers using t distribution instead of z distribution. So let's talk about t distribution, where it comes from, and then we're going to do this, okay? All right, so where does t distribution come from? Where does it come from? Well, in the past, when people tried to use the sample standard deviation s as the estimate for sigma, they proceeded and they realized that they ran into what? They ran into problems, because they realized that that distribution that they get is not a normal distribution. So the person who actually realized that, and the person who did something about it, was William Gossett, who was working for Guinness Brewery in Ireland. Now, his experiments with different types of beers, with hops and barley, produced very few samples, and then replacing sigma with s did not produce accurate results. So what he did, he realized he could not use normal distribution and for the calculations, so he found that the actual distribution depended on sample size, and he discovered a new distribution that's called the student's t distribution. The name comes from the fact that Gossett wrote under the pen name student. So now, up to 1970s, before the invention of calculators, when some statisticians used the normal distribution approximation for large sample sizes and used the student's t for small sample sizes, at most 30. With graphing calculators, of course, whenever we don't know sigma, we're going to use t. So we're not going to follow that tradition because we have technology. So the way we know whether we use z or t is whether we know sigma or not. If we don't know sigma, we use t. If we know sigma, we use a z. All right, so let me show you this distribution right here. You don't have to know the mathematical formula for it, but this is the mathematical formula for t distribution, and that's the mathematical formula for normal distribution. The red one is normal, the blue one is t. Now what I'm going to do here, I'm going to change the sample size, and as I change the sample size, you see that the blue graph approaches the red graph, and when the sample size is kind of close to 30 or more, right, you see that? Then the blue and the red are kind of the same. They're not exactly the same, but they're kind of become, so the t distribution becomes like normal distribution. But even if sample size is large and we don't know sigma, we are not going to use normal distribution, we're going to use t distribution. But that's the idea of the comparison of t distribution and normal distribution. As you see, as I change the sample size, so for every sample size, you see, we have a t distribution. See, for every sample size. All right, so going back here, so remember that if we have a population and we don't know sigma, then we take samples, right? And then we find x bar and we find s. And then the way we represent x bar is by x bar plus and minus certain number of standard deviations to the left and right. But what? Well, that number would be a t alpha over 2. And so what we do here, we assume that we take these x bars, right? And then we subtract from mu from it and divide by standard deviation of the x bars, right? So that's our t. And these t's make a distribution like that blue one right there, right? And so that's where t comes from. Now the question is, how do we get t? How do we know what t is? Because z, remember, we can get it with inverse normal. How do we get t? Well, we get it with inverse t. That's how we get it. So let's do that. Let's talk about that. So again, here's the big picture. Population with mu and sigma unknown. We take x bars, and then we convert x bars to t's right here. You see, these are x bars, and then we convert them to t's, and the t's make this distribution that we call t distribution with degrees of freedom of n minus 1, which is kind of a measure of the spread of this, but we don't call it the standard deviation. We call it degrees of freedom. All right. So, and this is again the math of where that x bar plus and minus comes from. And you can look at it. I talked about this before for z distribution, but basically that's what we have. If you think of the t distribution here, think of t distribution, then what we want here is basically, let's say 95%. Let's say we want 95% to be between what number and what number, right? So what are those two numbers? Those two numbers are going to be t alpha over 2 minus and t alpha over 2 plus. So basically what we want is that we want this t to be between this number and that number, right? We want it to be between those two numbers. How do we guarantee that this t is between those two numbers? Well, we have to put it there and say, okay, what's the probability that this number is going to be between these two numbers? 95%. So this is 0.95, and then we can isolate the mu in the middle just like we did before, and we are going to end up with this formula here. Okay. All right. So it's not that important to know that math. I'll let you read the conditions for properties of the student's t distribution. I already talked about it. I said that student's t distribution, just like normal distribution, right? The mu is 0, and there is no standard deviation. There is degrees of freedom, which is n minus 1, right? For every sample size, there is a distribution. All right, so, and let's see. So how do we do this with the calculator? Well, calculator also not only has, remember with the z, calculator, if you wanted to find if we have a Z distribution and we want to find the area between a number, let's say C and D right here, we could use what? Normal CDF. Now, if we had Z distribution and we wanted to know what is a number here that has this much to the left of it, we use inverse normal. Now we do the same thing. So with this, we do the same thing. So what are we going to do? We're going to do, so this is the T distribution. So T distribution with degrees of freedom of n minus 1, right? So how do we know what's the area between, let's say, C and D here? How do we find that area? Well, we go to something called T distribution CDF. See that? T CDF. Lower and then upper, right? And then degrees of freedom. That's all you have to put. So basically it's going to look like this. See, I'm going to do, where is my calculator? There you go. Oops, I have two of them now. Only need one. Can you do that with your calculator? Make 2 out of 1 quickly. Alright, so let's see. So let's go to distribution and we're going to go to T CDF, that one. And you see, suppose I want to know what's the probability that the number is going to be between, let's say, -2 to, let's say, 0.5, just, you know, made up numbers for C and D. And then all we have to do we have to put after that is degrees of freedom, let's say degrees of freedom of 14. So that would be 65%. That means if we were working with a T distribution with degrees of freedom of 14, then the probability that the number is between -2 and 0.5 is about 65%, right? All right. Now the question is, how do we do this if we have T distribution with certain degrees of freedom, and we want to know what's the number here that this much has to the left of it? Well, we do with inverse T. So let's use inverse T. So with the inverse T, we go to second distribution, and inverse T is right there. And so area to the left, let's say 5% to the left of it. And then degrees of freedom, let's say 14. So that number is -1.76. So the number here that has 5% to the left under the T distribution with degrees of freedom of 14 is -1.76. All right. All right, so let's continue. We talked about that already. Let's do an example. Here's an example. It says, find the t-score that has 90% of the area to the left of it. What's the t-score that has 90% to the left of it with the degrees of freedom of 10? So we go to inverse t, we put 0.90, comma 10, and that's what we get. All right. Now, if you don't have a calculator, you can use a table. So here's the table, and this column is degrees of freedom, and these tables are in the textbook. Oops, are in the textbook. If you click here, you go to the textbook and see it. But we don't really use tables if you have, technology. So let's say you go to 10, which is degrees of freedom, and these right here are areas to the left of the number. So we're looking for area to the left, 0.90. So 0.9 is the area to the left of this number. So 1.372 under degrees of freedom of 10. So notice that that changes if the degrees of freedom changes. See that? Alright, so that's how we use the table if you want to use it. There is a notation for t-distribution. That's the notation. T has t-distribution, and the only parameter you need is degrees of freedom. And we put that parameter as a subscript of t. So when you see something like this in statistics, it means a t-distribution with degrees of freedom of 19. Okay? That's not sample size. That's n minus 1. So that's 19. So if you see this, that means the sample size must have been 20. All right, so I talked about this again. We know that we get the, so when we find x bar from the sample, we're going to add and subtract t alpha over 2 times what? S over square root of n. So that's how we do confidence interval. All right. So here is an example. This time we are given raw data. So what we need is basically we need this. We need to know x bar. We need to know t, and we need to know s over square root of n. All right, now x bar, of course, we have to put all of these in L1, right? We have to put all of these in L1, and then go to one variable stat calculate, one variable stat, and then enter, L1 enter. So you get the mean, and you get S right here. So that's how we get these two, right? So we got the mean, which is what? Which is 8.2. So 8.2267 plus and minus. Now we're going to get to t in a second. S is 1.67, let's say 22, divided by square root of, what is the sample size? 15. Now here, what's the confidence level? Well, confidence level is given here for 95%. So we want to be 95% confident. So we have to go to the t table, right? And then we're going to have, we have to find two numbers that they have 95% in the middle if we have t-distribution with degrees of freedom of 14, because n is 15, right? Okay, that's easy. So how much is to the left of, let's find this number first. Because if we have this number, then we have the other number too, because that's easy to find. That's just the positive of this number. So how much area is to the left of here? Well, 95% is in the middle, so there's 5% left for the tails. So each of them takes 2.5%. Now 2.5% is 0.025. So we are going to go to the calculator, inverse t. So let's go to inverse t. We had it there, but I'm going to go to it one more time. Inverse t. And I want 0.025 to be to the left. And I want degrees of freedom to be 14. There. So negative 2.14, right? Negative 2.14. 447.8 if you do 4 decimal places. So that's what it's going to be. So this number right here is going to be, what was it? We lost it. Put it right there. So that number right there is going to be 2 point, we don't want the sign, right? 2 point, because we already have plus and minus here. 2.1447, and you have to multiply that. That's it. All right? So that's what we're going to get. I use 14.7, but this is 2 decimal places. So the error would be that much. So we have to add and subtract this error to x bar, right? Remember, what I had was x bar already, plus and minus t alpha over 2, and then times s over square root of n. All of the stuff here is given by that, right? And then x bar, of course, is, what's x bar? Is that right there. That's x bar. All right. So the interval is that right there. That's the interval from 7.3 to 9.15. Now we could do this directly with the calculator. So the way we do it is we go to, just like with the calculator, we could go to z interval. Now here you have to have the numbers in L1. I don't have them in L1 in my calculator right now, but I'm going to show you how to get there. So you put the numbers in L1 by going to Stat, Edit, and you put them in L1. I don't have them in L1, so, but I can show you. So once you have the numbers in L1, then all you have to do is go to second distribution, my fault, go to Stat, Tests, and under Tests, we want to go find T interval, that one right there. Now when you go to interval, they ask you whether you have a stats or you have data. In this case, we have raw data, right? You see, we have raw data. So once you do that, then it says, where is the data? Is there a frequency? Sometimes there are frequencies. There's another column of frequency, how many of each you have. But in this case, we don't. So we're going to leave it like that, 1. And the level of confidence in this case is 95%. So change that to 0.95 and calculate. You see, in a matter of second, maybe fraction of a second. So what does the calculator do for you? Calculator do all that for you, does all this for you. X plus and minus t s over square root of n. So calculator knows n because from L it gets n. Calculator knows this because it gets it from here. Calculator knows this, it gets it from its memory. Calculator knows this because it gets it from your sample. And then it's going to give you the answer, which is what? That interval right there. So calculator does that, all that for you. All right, so let's move on. Here's another example, and I'll let you do this yourself. Answer this question yourself. The numbers are just a little bit bigger, but I'll let you do this yourself. I'm going to move on to the next example. Now there's a good video here you should watch, and goes through the history of where the T distribution comes from, and in fact, ironically, they go to a brewery to talk about this concept. It's an interesting clip. You should watch this. All right. So let's talk about proportion. What happens if the the population? Let me see if I can write here. So the mu this time is not known. Is not something we want. We want the proportion. So proportion is basically what? Number of successes divided by the population size. For example, in Houston area, you want to know what percentage of people live in apartments. Well, you go to Houston area and you have to count everyone. Can you count everyone? Now it's kind of hard. So we don't really know this because there's so many people live in Houston. But we can take a sample of Houston residents, right? Randomly. And then find what? Find P prime, right? Now, the question is this P prime the same as that P? Well, obviously not. So what do we have to do? We have to do the same thing we just did for mu. So we have to do P prime plus and minus certain number of standard deviations times the standard deviation of the P primes. Now, what is the standard deviation of P primes? Well, we know that we know that p prime is x over n. So that means basically x has a binomial distribution. So x has a binomial distribution, and in a binomial distribution what we have is n and p, and the mu of the binomial distribution is np, and the standard deviation is the square root of npq. Now p is nothing but x divided by n, so the distribution of p primes, basically the distribution of p primes will have mean of p primes would be basically the mean of x divided by n, which is just p. So the mean of p primes is just p of the population, and the standard deviation of the p prime, standard deviation of p primes, would be standard deviation of the population divided by, the standard deviation of the x divided by n. So npq, and then divided by n. Now if you put this n inside the square root, you would have to square it. So we have npq, npq, npq over n squared, and n cancels one of these. So we end up with standard deviation of p primes is square root of pq divided by n. Now obviously we don't know p and q, so what we're going to do, we're going to use p prime and q prime. Now that is going to cause a little error, but that's okay, we can take care of that later. Alright, so that's all there is to it. So what we have here basically is, this is going to be a normal distribution, so we can convert the p primes to z and do the same thing we did when we used z interval. So we're going to take p primes and subtract the mean from it and divide by standard deviation of p primes, which is going to be basically that. And these are p prime and q prime. And then this is going to give us z, and the z's of course are standard normal. Then to find the numbers that we have to go to the left and right, well, we just use z alpha over 2. So that's the same as before, z alpha over 2. But the standard deviation is this new standard deviation, which is p prime q prime over n square root. So that's how we write confidence intervals for proportion. That's all there is to it. So let's do some examples. So here's the big picture again. I just explained all this. You can take a look at it one more time. Let's do some confidence interval. And that's the same thing I did 2 times so far, just isolating p in the middle. It gives you that formula p prime plus and minus that, right? So you don't really have to derive this. You just have to be able to use that formula we just talked about. But you can take a look at it and do a little algebra and you can get there, right? All right. So again, we talked about all that. You should read this one more time. And that's the conclusion that we have, that p primes are normally distributed with the mean of p and the standard deviation of this right there. All right, so the error bound here, what is the error bound? Well, the error bound is where we got p prime, right, plus and minus, certain number of standard deviations, which is square root of p prime q prime over n. So that is the error, right? So in all of these, remember, in all of these examples, we have x bar plus and minus some error, and then we have p prime now plus and minus some error. Now this error, we call it the error for the mean, and this one is error for the proportion, right? So that's the idea of error. All right, and this error, the formula is that, and the error for x bar depends on whether we use z distribution or we use what? We use, if we use normal distribution, it will look like that. And if we use t distribution, it would look like t alpha over 2 and then s over the square root of n. See? All right. So let's do an example. Suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. Find 500 randomly selected adult residents in the city are surveyed to determine whether they have cell phones. Of the 500 people, 421 responded yes. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents of this city. Okay, so what we have to do is we have to think of this formula, p prime plus and minus some z times what? Times p prime is square root of p prime q prime divided by n. So what is p prime here? Well, p prime is 421 divided by what? 500. That's what p prime is, right? Plus and minus, because p prime is what? P prime is that 421 here divided by the 500. So now what is z? What is z for 95% from normal distribution? We know that's 1.96, right? And then we're going to put p prime and q prime here and divide by 500. Now p prime is 421 over 500. Q prime is 500 minus 421 is going to be 79, right? Because you know q prime is what? Is 1 minus p prime. And that's it. So we're going to have to do this with the calculator and find it. Now, we could also use calculator for the whole process instead of doing all that. So what we can do, we can go to, again, stat, tests, and then we go to one proportion z interval. You see that? One proportion z interval. Now, all you have to do here is put what your x is here. What is our x? What? 421? Okay, that's right. And what is our n? 500. And what is our level of confidence? 0.95. And there. That's it. So if we were to put this in the calculator, we would find that this minus all that would be 0.81003, and this plus all that would be 0.8397, right? So that's all there is to it. And those are the two numbers you see right here. Let me erase. And that's what we got, right? 0.81 and 0.874 right there. All right, so that's all there is to it. And again, using the calculator, I just did it for you. You can take a look at this again, but I just did it for you. All right, now here's the problem. If we use this remember what we are doing here. We are using, um, we say p prime plus and minus z alpha over 2 square root of pq over n, but we don't have p and q, we have to use what? P prime and q prime. Remember, if we didn't have sigma, right, if sigma was unknown, then what did we do when we took a sample? Well, we used S instead. So using S instead of sigma caused the problem, and the problem was that the distribution wasn't normal, so we had to use T distribution, right? Remember that? Now, what kind of problem this is going to cause using Q prime and P prime instead of P and Q? Well, it turns out that the problem is not a very big one. We can easily resolve the problem. All we have to do is just add 2 to the number of successes. So add 2 to the number of successes and add 4 to n, and that's it. This method is called the +4 method. And computer studies have shown that this actually works. So it takes care of that error. So in this course, if you're told to use the +4 method, then before you do the proportion problems, you have to make this change right here. Add 2 to the number of successes and add 4 to the number of to n. If you're not told to use +4, just do it the same way that I just did, right? All right, so that's all there is to it. As I said, computer studies have shown that this method actually is effective. So it should be used when the confidence level desired is at least 90% and the sample size is at least 10. Those are conditions. Okay, so here you go. So a random sample of 25 status students was asked, have you smoked a cigarette in the past week? Six students reported smoking within past week. Wow, can't believe that. Use the +4 method to find a 95% confidence interval. So what we have to do is we have to write p prime plus and minus sum z times the square root of p prime q prime over n. Now, p prime, before we do it, normally we have x and n, right? So what is our x here? Our x is 6 and our n is 25. So before we do that, we're going to forget about this x. We're going to use this x. X is 8. And we're going to forget about this n. And we're going to use what? This n. Add 4 to it. Now, everything else is the same. So we can do it with the calculator, actually. So let's do it with the calculator. I don't know why. Oh, there you go. So let's use a calculator. So what I'm going to do again, I'm going to go to stat tests, and I'm going to go get what? 1 proportion z test. And instead of x, what do I put? Did you say 6? No, you didn't. 8. And n, did you say 25? No. And what is the confidence interval? 95% again. All right, to calculate. There. That's what we're going to get. So it's between those two numbers right there. Okay? So between 0.113 and 0.439. And again, if you put all the numbers in here in the formula, you get the answer. All right? So let's continue. So that was the +4 method, right? Now the question is, suppose you want to do a study like this. How do you know how many people you should put in your sample? So how do you know how many people you should put in your sample? Well, you don't know. So what do? Well, we know the error is given by this formula, right? Now, what do I mean by error? I mean like p prime plus and minus some error. That's the error, right? So we're going to say, let's call that E, and then isolate n here. So if we know what error we like, let's say you don't want to be off more than 3%. So for the error, you put 0.03. And then you know how confident you want to be. Let's say I want to be 95% confident. And then we find n. Now, the problem is we don't know p prime and q prime, and we're going to talk about how to get those in a second. But for now, if we know p prime and q prime, then n can be found here easily by a little algebra, right? So square both sides, right? And then just switch these two, right? In algebra, you can do that. If you have a number equal to a fraction like this, you can switch those two. If you cross multiply, that's the same thing. If you multiply this by 1, this by n, that's what you're going to end up having. So this is the formula for n. If you want to know what n is, that's the formula right there, right? So this comes from how confident you want to be. This is just the error. All of those three letters are just one number, right? Is the error, like 0.03. Now remember, if the error is 3%, don't put 3 here. You have to put 0.03 here. Okay? And p prime and q prime, we're going to see that we have two numbers for them in a second. And those two numbers are just 0.5 and 0.5. That's all you have to do. Just put 0.5 and 0.5 for p prime and q prime. If you're not given p prime and q prime. If the problem is given p prime and q prime, then you use the given data, the given information. If you're not given p prime and q prime, just use 0.5 and 0.5. The reason for this is that if you have two numbers that add up to 1, and you know p and q add up to 1, p prime and q prime, right? Now, if you multiply two numbers that add up to 1, the maximum number that you can get is actually 0.25. And you can prove that algebraically. And I have the algebra if you want to look at it in the next slide. But just if we take that as, true, then we say, okay, the maximum contribution to this formula that p prime and q prime can have is just when there are 0.5 and 0.5. And the maximum contribution would be 0.25. All right, now we have a formula, and this is the algebra. Y, if you want to, you can see it. But not important to actually derive this. All right, so here's a problem. It says, suppose a mobile phone company wants to determine the current percentage of customers age 50 plus who use text messaging on their cell phones. How many customers age 50 should the company survey in order to be 90% confident that the estimated proportion is within 3 percentage points of the true population? True population proportion. So what we have here is basically the formula that we had. Remember the formula? The formula was that right here. Where am I? Here we go. So the formula is right there. And all we need is Z. So for 95%, how confident do we want to be? 90%. So for 90%, our Z is 1.645. And P prime, we're going to put 0.5. Q prime, we're going to put 0.5. And for this number, we're going to put 0.03. Don't put 3. 0.03. And we get this number. Now, how do we go about sampling 751.7 people? Well, we can't do that. So we have to always round up. So to the next integer. So 752. So if you have 752 in your sample, that guarantees that your error won't be more than 3%, right? So that means when you give your interval cannot be off more than 3%. So you accept 3% to be the error that you can have. And if you look at, when you hear in the news or in newspapers, when they talk about proportions, they always give plus and minus certain percentage, and that's what that is. That's the error. That is the error that goes on the right hand side, plus and minus some error. That error could be up to 3% off, right? All right, so again, I want to review this quickly. There did 3 different things in this chapter. We did confidence interval for mu when sigma was known, and that's the formula. And with the calculator, we go to z interval to do this. And then if sigma is not known and we are looking at mu, then the interval is given by this formula. The difference is that instead of z we have t, and instead of sigma we have s. And with the calculator, the way you do it is t interval. And both of these situations, you can have raw data or you can have the statistics. If you have the statistics, then you pick a stat. If you have raw data, you pick data. And then for proportion, we use this formula, and with the calculator, we go to 1 proportion z interval, right? So the calculations are very easy in this chapter because calculator can do it for you, right? And there are 2 more formulas, one for finding the sample size if you're working with proportion, and finding the sample size if you're working with mu. All right, there is another video for confidence interval here, intervals, and you can watch that yourself. So we are done, and there are some problems to just practice on for the final exam. And that's the end of this video. So I'm going to see you, let me first see you right now, and so I see you in the next video. Well, actually I've made the next video already, the chapter 9 part A, and so here's chapter 8, so end of chapter 8. All right, take care of yourself and others, and I'll see you in the next video.